All right, so I'm diving into the next example on this two-part optimization series. And this is a pretty tricky one, but you're going to see it's not too bad. It looks worse than it really is. So let's just read through it. A box is to be made from a 3 foot by 8 foot rectangular piece of sheet metal by cutting out squares of equal size from the four corners and bending up the sides. Find the maximum volume the box can have. Okay, so I see the word maximum. So that definitely tells me this is an optimization problem. Um, definitely tells me. So, like I said, let's just first draw a picture. And I know you're seeing this. You're seeing this this problem, and you see like these dimensions, and the things are getting cut out of corners. You're like, holy crap, like that's just a lot to deal with. But just trust me when I say it's not as bad as it really is. So I got a box, right? I got a box, and it's 3 feet by 8 feet. So I'm just gonna call that 3, and this guy over here will be 8, 8, and it says that the corners basically the corners are getting cut out and then bent up. So I'm basically just gonna kind of show what is going on. I'm gonna kind of put dotted lines to signify that these corners are getting cut out. So there's one, there's two, and then again, and these are supposed to be squares. They're not as even. They look like more like rectangles, but it's okay. You get the point. Um, okay, so what I want to do here is I want to label the unknown distances with something. I want some variable to represent this. So I'm going to label these little boxes, X's. X on him, X on him. These little boxes, they're little squares so that they both have equal sides, just X, X. And that's X all around. There's X here, X there, X here, X there. You get the point. There's just X's all around. These boxes are getting cut out. And X here, X there, so on and so forth. You get the point. Okay, so what are we being asked to maximize? What are we being asked to maximize? So we did the first step. We drew it. We did the second step. We labeled it. Now let's kind of set up what we need to get. Let's set up what we need to do. So my volume, we're being asked to maximize the volume, right? So that's my maximizing function. My maximizing function, or the master function, if you want to call it that. Maximizing function. Maximizing function. It's volume. So V equals, well, what's the volume of a box? It's just length times width times height. Length times width times height. Okay, and now let's just kind of try to figure out what this is. So don't be so quick to say 8 and 3 and so on and so forth as your length and width, because you got to remember what's happening at the end of this. Remember that these pieces are being cut out and then they're folded inward. This side right here, this side, it's getting, these four are getting cut out. Like once this box is done, this is no longer going to be here. Neither will this, right? Neither will that, neither will that. Those will not be a part of the box anymore. Those pieces are getting cut out. So what's its real length and real width? Well, its real length, we have 8 here, but I can just subtract an x and another x, because think about it, when this box gets made, these two are going to be gone anyway. Those will no longer contribute to the length. So I have an x that's no longer going to contribute, and I have another x. So I have two x's. So once this box is done, my length won't just be 8, it'll be 8 minus 2x. 1x for here, 1x for there, because when this box gets cut up, these distances will no longer contribute to that distance of 8. They will be gone. Likewise over here, I have 3, a distance of 3 over here. This will get cut out, this will get cut out. So a length of x will get cut off, and another length of x will get cut off. So my width, it's not 3, it's 3 minus 2x. 3 minus 2x. And then what about my height? Well, the height's the easiest part, because remember what's going to happen here. These are going to get cut out, and this end right here, this, I wish I could show an animation or something. This is going to get folded up. This this guy right here, it's going to get folded upward. So what's really going to happen is that since this box is it's getting folded upward, like imagine that you're taking this portion right here and you're pulling it towards you or something, like from the right hand side, you're just pulling it towards you. Then you're going to see that this becomes the height. That becomes the height, just that x. So my height is just x. And you can see here, setting it up is really the tricky part. That's really the difficulty here. So again, let's just go over this really quickly, just again to kind of nail it in. I have this whole length was 8. This whole length on this side was 8. Once this box gets cut up though, I will lose an x. I will lose this portion in red. So I'll lose this distance of x and I'll lose this distance of x. So I'm going to lose a total distance of 2x on this side. So this whole part is going to be 8 minus 2x. 8 minus 2x. Then again, for the width over here, this distance will be cut off, this x will be cut off, and this will be cut off because both of these squares will be getting cut out. So this over here will be 3 minus 2x. 3 minus 2x. Okay, and then my height, because once this gets cut off, then this portion, this inner portion right here, it's going to get pulled upward. It's going to get pulled upward. So my height is just going to be this part. This part is going to get pulled upward. So it's going to be just x as my height. X as my height. Okay? So that's my volume. That's my volume function. And then we ask ourselves, hey, do we need a helper function? Do we need a helper function? Well, the answer is no. Because remember what the purpose of the helper function was, like I said in my last video. The helper function is to only help you get your maximizing function in terms of one variable. But if we look at our maximizing function, we say, hey, it's already one variable. We don't need to do anything else. So the helper function is just not needed. Not needed. Not needed because max function is already in one variable. It's already in one variable. If it were in two variables, x and y, then I definitely need this helper function, but it's already taken care of. So I don't need it. I don't need it. And that's what I meant earlier when I first said this. Like, you use the helper function if needed. In the last example, in my last video, we needed it. In this example, we don't need it. So, that's what I meant too when I said this problem's harder and easier at the same time. It's harder to set up, but it's easier because we don't need to worry about the helper function. So okay, now we just do what we've always done, right? This is v of x, and now it's just some basic algebra. So I'll just do that really quickly. 8 times 3 gives me 24. 8 times negative 2 minus 16x. Negative 2 times 3 minus 6x. Negative 2 times negative 2x plus 4x squared. And then times that x out there. Okay, let's just clean this up really quick. This 16 and this negative 6 will combine to be negative 22x. So distributing this x now to all of these terms, then I'm going to get v of x is equal to 24x minus 22x squared plus 4x cubed. Okay, so now I just take the derivative. So remember that was the next step. Once we set this up, we take the derivative. So v prime x is equal to 24 minus 44x plus 12x squared. So now what I have to do is I have to find the max and the min values, local max, local min. And this is just from the earlier sections. It should be, a few sections before what you do before optimization in your calculus book. So I'm going to write this in descending order. I don't really like my x squared at the back. It just kind of makes me uncomfortable. So 12x squared minus 44x plus 24. And I just got to factor and solve for x. So let's do that. If this is you're also a bit rusty in your factoring, I encourage you to watch one of the first videos I made that deals with, it's called factoring by the AC method or something. Deals with scenarios just like this. So if you're rusty on your factoring, I encourage you to check that video out, and it should help you quite a bit. So I'm going to factor out my GCF. My GCF in this case, it should be just 4. So I'm going to get 4 times 3x squared minus 11x plus just 6. Plus just 6. And then, I'm going to factor out a 4 on both sides just to get him to go away. And I get 0 is equal to 3x squared minus 11x plus 6. And now I'm just going to do that factoring by the AC method. So AC is equal to, 18, A times C, 3 times 6, 18. B is equal to negative 11. So remember, a number that adds to B multiplies to AC. And I'm going to get negative 9 and negative 2. Negative 9 and negative 2. So I'm going to rewrite that middle term. 3x squared minus 9x minus 2x plus 6. And then I'm just going to factor by grouping. And if I'm going a little fast on this, I encourage you, to watch that video I was talking about. I do slow down for that. I'm just kind of speeding through this because at this point, you should be pretty comfortable with your factoring. If not, though, I really do slow down in the other video, so check that out if you need to. Okay, so 3x times x minus 3, and then a negative 2, and then x minus 3. Perfect. And so this becomes 3x minus 2 times x minus 3 is equal to 0. And then I just set both products equal to 0. I set both factors equal to 0. So 3x minus 2 equals 0. X minus 3 is equal to 0. And I'm going to get x is equal to 2/3. 2/3. And I'm going to get x is equal to 3. X is equal to 3. So now you can see that we're running into a bit of a problem. We're definitely, we have two values. Last example we had just one, but we have two values. And remember what I said, when you have a couple different values, you have to see, hey, which one's the max, which one's the min. Because our problem, right now it's asking us to find basically the maximum volume. And well, we would basically take this and plug it into our volume function, but which one? Are we plugging in the 2/3 or the 3? And that's up to us to find out. So I'm going to try to resize this. I've never done this before. I don't know if this is going to completely erase the board. If not, then so be it, but we'll see. So let's see. Okay, it didn't. It's just very zoomed in though. Let me just undo that. Just undo it. There we go. Okay, so I'll just do it. I'll do it over here. I still have some room. Okay, so I have x equals 2/3 and x equals 3. So I have to find out, hey, which one is the max and which one is the min. So I'm just going to draw this little number line. You might have your own way to test it. I'm just really kind of using the first derivative test right here, seeing which one produces local max, local min, that's all. So plugging in values to the left of 2/3, and then this is just f prime x down here, f prime. Okay, so plugging in some values to the left of 2/3 into my derivative function up here, we can just think, I'm going to plug in on a calculator right now. 24 minus 44 times, I don't know, let's just say negative 55 plus 12 times negative 55 squared. And I get a positive value, and I get like 38,000 something. Okay, so it's positive. It's positive. And then let's try some value between 2/3 and 3. I'm just going to go with 1. Pretty straightforward. 24 minus 44 times 1 plus 12 times 1. And I'm going to get a negative value. I'm going to get negative 8. So negative. Okay, and then let's just try a value to the right of 3. Let's just try 100. So 24 minus 44 times 100 plus 12 times 100 squared. And I get a positive value, and I get 115,624, so it's positive. Okay, so I look at this, and I see, well, which one's producing the local max, local min? So here, it's positive, so it's increasing, cap out, and then it's decreasing again. Here, it's decreasing, bottoms out, and then increases. So this one is the max. This one is a max. So you can see that, hey, x equals 2/3. That's the winning ticket right there. X is equal to 2/3. That's the one that's going to give me my maximum volume. So now we're in the home stretch. I'm just going to, so x is equal to 2/3. And if it were asking us, like, hey, what x value, what height is the maximum, we could just say x equals 2/3. But it's asking us for the maximum volume. It's asking us for the maximum volume. So I'm going to plug this into my volume function. I'm going to plug 2/3. I'm going to plug 2/3 into my volume function. So my volume function was just, as we defined earlier, it was 24x minus 22x squared plus 4x cubed. So I'm going to plug that in. Okay, so 24 times 2/3 minus 22 times 2/3 squared. Sorry, and I'm really stretching for room right here. Plus 4 times 2/3. And if you do all of your calculations correctly, I'm just going to do this really quickly on my calculator. 22 times 2/3 squared plus 4 times 2/3. Okay, so 24 times 2/3 minus 22 times 2/3 squared. Okay, and then, oh, sorry, that should be cubed right there. Okay, and then you should get 200 over 27. 200 over 27. I'm going to double check that on my calculator really quickly. Make sure I did all of that right. 2/3 squared plus 4 times 2/3 cubed. Cubed. Okay, yeah, and I get 200 over 27. That's the right answer. And you can, so basically you see here that I just plugged 2/3 into this function right here. I just plugged 2/3 into this. Wherever I saw an x, I put a 2/3. So I just basically substituted. I put 2/3 in for x. 24 times 2/3 minus 22 times 2/3 squared plus 4 times 2/3 cubed. And that's exactly what I have here. So, and then we have to just basically look what values or what units are we using. Well, we're working with feet, so I'm definitely gonna have feet, but we're also working with volume, so it's feet cubed or cubic feet. And that's our answer. That's the maximum volume. So this one was definitely a bit more involved. Took up a bit more room than I expected, uh, but it wasn't too bad. Um, Really, the tricky part about this, you can see that after we found, after we set this up and drew our picture and got the logic nailed down, it was really a pretty easy process. It was really just, you know, find the derivative basically, find the max and min, and then from there, we just did what we've always done before, and you just get some value out of it. And this is the maximizing volume of this right here. This is the maximum volume that basically we get for some x value. So hopefully this example definitely cleared some things up for you. I feel like that this one and the last one were both pretty good examples. The last one was good for, getting you into the rhythm of working with optimization problems, setting up a maximizing function and helper function. And that one was really quite easy though. This one though, is definitely more involved. Definitely requires a bit of thinking, especially when we were thinking about setting this up. And it requires more thinking in that, you can't just stop when you have 2/3 and 3. You have to see which one is going to produce that maximum volume. We find it, and then we plug it into our volume function, and we get the answer, 200 over 27 cubic feet. So hopefully this was helpful. If you want me to do any other particular optimization problems, feel free to message me. I'm always more than happy to help. But as always, thanks for watching.